The idea was first brought up by Barbara Liskov in 1987 in a paper about substitutability. This design principle, or I'm going to say goal of our design, is probably the most important of the acronym SOLID. This is what leads to highly flexible frameworks that allow extensive changes to our application. Now, this primarily relates to inheritance. Now, many designers and programmers mistake the tool of inheritance as a reuse tool, and while it's true that we do inherit some things from the base class, that's not really our primary goal. In fact, what we want to do is override much of what we inherit from that base class. Now, the real goal of inheritance is to provide an abstract data type that we can use in algorithms where subtypes or derived types can be substituted for that type within that algorithm. We want to build the majority of our code in our application so that it's written towards the abstract type and completely unaware of the derived or concrete types in our application. This means that the base class needs to look a lot like the concrete classes. If you find yourself having to downcast, then you're kind of missing the point of this substitutability, which is the main reason that we have inheritance. In fact, I would say that we should never downcast in an application. That is, cast a variable of a base type down to a derived type, just so that we can call a method that's only defined in that derived class. All right, now let's take an example of an application requirement where a landscaper needs us to build an application so that they know the total area of a homeowner's lawn. Now, the lawn is made up of rectangles and triangles and circles in various shapes that we'll probably need more of later on. Now, the landscaper wants to know not only the area for a homeowner, but also maybe the area of a bunch of homeowners that they have on their route for that day. Now, if we recognize that the concrete types or classes are circle, triangle, rectangle, etc., then we might also realize that they all derive from a common base class called shape. If we can create a method that loops through all of the shapes in an array or a collection and calculate the total area. So given that, we'll need to create our class shape so that it has a function called getArea. That function, of course, will be overridden by all of the subclasses. Now let's just keep things simple. Our shape class will simply have two properties, a width and a height. The shape class will also define the getArea method. Now, our concrete classes will simply override the getArea method and provide the appropriate calculation. The classes inherit some simple implementation from the base class, the length and width, and some getters and setters for that, but that's really not that big of a deal. It's just a few lines of code, so we're inheriting some implementation as well as the instance variables for that. The real benefit is what we'll be doing with the classes that use the shape class. So the code that benefits from that substitution is going to be our class called landscape. So let's say that a landscape is an aggregate of a bunch of different shapes that make up a homeowner's lawn area. So we can loop through all of the shapes that are in their collection and calculate the total area that way. This code would only know about the shape class and would have no need to know about the derived classes of circle and rectangle. Now, if we were using this example a little incorrectly and felt like we needed to know the radius of the circle in order to calculate the area, then you would find yourself downcasting all of your shapes to whatever their appropriate type is so that you can perform the computation. Rather than perform that computation in the landscape class, however, we're going to push that computation into the individual circle, rectangle, and triangle classes. Now, the landscape's getArea method is going to loop through and compute the area of each individual shape by simply calling their getArea function. The landscape class is only dependent on the shape class. So if we need to add trapezoids later, then it's just a matter of creating that class as a subclass of shape, and we can substitute trapezoids for shapes within the landscape algorithm. At compile time, the compiler knows about getArea in the shape class. Because we never reference any of the other classes from landscape, it doesn't know anything about those. In fact, circle and rectangle and triangle don't even have to exist in order for us to create our landscape class. So later, when we add trapezoid, that provides that substitutability. Now at runtime, however, Obviously, the runtime does not invoke the shape class's getArea function because it doesn't even have lines of code in it. But at runtime, we're going to select whatever object type is on the left-hand side of the dot and call its getArea method. This is called polymorphism, which literally means multi-shaped. But in a type system, what we mean by polymorphism is that there's multiple behaviors associated with a single type. One note about the substitutability principle is that it does require both semantic and syntactical compatibility. In other words, it's not enough to just create the getArea function in your derived class. It also needs to perform in a substitutable way as well. If you create a subclass of shape and implement the getArea method so that it throws an exception, then that would be violating our contract of substitutability. So it's very important that within a family of classes that inherit from a base class, not only have syntactical substitutability, but also have semantic substitutability. Now, in our next topic on interface segregation, we're going to take this landscape design a little bit further. So press the subscribe button below to make sure you don't miss out on any future episodes in our design and programming topics. Also, check out the description below for deep discounts on our programming courses at Udemy. We are adding new courses all the time, so check back often. Hey, I'm Chuck McCullough, and as always, code happy.